Welcome to the Oakgate Test Solutions Power Loss Prevention and Data Validation Training. My name is Dave Obert, and I'm the Oakgate Products America Sales Development Manager. I'll be your trainer for today. If you have any questions about this training, about Oakgate in general, how to buy an Oakgate, please feel free to email me at the email that you see here on the screen. I'll be happy to help you. This training is going to assume you understand the basics around discovered appliances, starting a slot, configuring a controller, and defining traffic with the I/O exerciser. If you're unfamiliar with those concepts, you may want to go back and watch our basic use video and understand kind of those three main steps, and then jump into the power loss. The other caveat here is dual port drives have their own nuances. We're going to do this training focusing on single port drives, and for dual port drives we'll cover all those nuances in the dual port drive section. Okay, with that being said, the first thing we need to do to be able to toggle power, we need to attach a peripheral, and we're going to do that by clicking on this plus peripheral button that you see right here. This little window will come up. When it comes up, we're going to specify the appliance we're using, and in our case we're using OGT Demo, and then we need to specify the peripheral type, and you'll want to know this. So is your drive sitting in an Oakgate 4-bay or a 12-bay? Might it be a add-in card sitting on top of an interposer, or it could be a drive sitting in one of our Daichu ovens. All these are different options. If it is sitting in the Daichu oven, you're going to need to specify the IP address, which you typically can get right here from the Discovered Systems tab, and you'll need to specify the type of device it is. In our case, as a 4-bay, we just have to go up to the Oakgate 4-bay, 12-bay, determine do we want all the slots powered on or not, and then go ahead and hit connect. Once we hit connect, the peripheral will become connected and show up in this window over here on the left. So we'll go ahead and close this window and spend a little time on the connected peripherals. The 4-bay modules, the 12-bay modules, the Daichu ovens, and the interposers all measure power, as you see here. From the Configure tab, I can go ahead and cut power, and as you see, it cuts power to the drive. I can also toggle PERST in addition to turning power on and off, and I can define what I want to do with PERST on a power cycle. Generally, you will pull power as part of a timed sequence, and you'll do that within I/O exerciser itself. There are instances, if you want to pull power doing things like downloading firmware, you can only do that via Python, and you would toggle power via the configuration tab when you're doing something like that. For our purposes, we're going to toggle power as part of time power when running traffic, so we want to get ready to pull up the exerciser and be able to define traffic. Now before we do that, there are some preferences that we're going to want to set. So one of those preferences is in your data validation settings. I'm going to turn these all off, and you can see it gives me options from disabled with no memory usage all the way up to 8 bits with high memory usage. The default is going to be verify discarded trimmed blocks. If I want to verify diff, then I lose the ability to do 2, 4 is the minimum I can use. If I want to verify overlapped writes, now I have to do 8 bits, and in addition I can do write zeros or write uncorrectables. Overlapped writes come about because the Oakgate system is not a file system. We are sending packets to the drive at a high rate of speed, and some of those packets may overlap. So if we want to verify that the entire packet was written to the drive or none of it, then we have to keep track of the sequences of writes to the different LBAs and make sure that everything lines up correctly. To do that, the depth of which we can manage the overlapped writes comes into play. Previously, OakGate, when it was only 2 bits, could only keep track of 2 overlapped writes. And so if you had an overlapped write, you could get a data validation error that wasn't really a data validation error. We have since enhanced it, but that enhancement does require more bits of memory to use. And so more advanced, better data validation settings can have an impact on the memory. To get a sense of how much data validation can impact memory, we're going to turn to our memory configurator, which currently is set at a standard 4 drives, with each a single namespace and a controller attached. It's a 6 terabyte drive with 512K block size. In this instance, with the standard default older data validation model, you can see we're using only 16 gigabytes of memory, which is not a terribly large amount. But now watch what happens to this field as I start to change the data validation and add some of the new capabilities. So as I go to diff, it jumps up to 33. As I go from 2 to 8, it jumps up to 66. And as I start adding trim ranges, it goes up even further. And so you can see all of a sudden I need 66 gigabytes of memory in my system to be able to do the data validation with all those capabilities. Now, some of your older Gen 3 systems or even Gen 4 systems, which often came out before these data validation enhancements, may not have all the memory you need to perform these data validations, but you can upgrade the memory. Your Teledyne LaCroix sales rep can help you do that. And if you're getting a new system, we recommend that you walk through your memory requirements with them before ordering your system, so you ensure that your system has enough memory for the drives and namespaces and data validation you're looking to perform. Let's go back to our application. We set our preferences. We've attached the peripheral. And we're going to go back to the Discovered Appliances tab and start our slot. And that will bring up our controller over here in this window and allow us to go to the Configuration tab and start to configure our DUT for data validation settings. When doing PLP testing, there's a couple things that you may want to think about setting in addition to any queues or namespaces that you may be doing. The first one is what's your expected link speed. If you're going to be powering down the link and then bringing the link back up, you may want to verify that in fact the link is coming up as you expect. If you set the expected link speed, and here I've set it for a by 4 Gen 4 drive, the OK software will in fact verify that the link speed has come up as expected, and if not, it will send an error or put an error in the log. The other thing we need to do is we need to associate the slot with a particular controller. There's no way for the software to know which slot this controller resides in, and we need to tell it so that when it pulls power on your drive and not your workmate or your colleague that has been running a test for the past 48 hours. So again, it's helpful to come back to my chassis and look at it, right? This will tell me what is the module. It'll tell me what slot I'm in, all those kinds of things. And so I see here I'm in slot 1. And so I'm going to come to my configuration tab. I'm going to hit add. I'm going to go to this host card, Peripheral Module 1, and I'm going to hit OK. And it shows the peripheral module, says ready to associate. And at this point, when I go ahead and initialize it, the drive will come up and power will be associated with that particular slot. In my case, I'm going to change one other thing here. I'm going to change this to MSIX. And then I'm going to go ahead and initialize my drive so I'm ready to start defining traffic. And you can see my namespace has come up and I'm ready to start with the next step. So for the next step, we recommend using automation, and this brings up the automation tab, to create your disk prefill subroutine. And you can call that disk prefill subroutine as part of a Python test, or you can use it just as the start for any data validation automation test you want to create. So to create that, again, we're going to go to Automation Settings, and we'll start with the top level, and we'll just call this Disk Prefill Subroutine. We may want to say, I want to auto-associate all testable units. This will apply it to all units that are in there, or you may not want to. If you're going to use just a subset of drives, you may want to manually associate the drives, and we'll talk about that later. So for now, we're going to manually associate our drives, and we're going to come in and create our disk prefill test set. So in the disk prefill test set, the first thing we're going to do is we are going to add an action. And within automation, I can add a range of actions such as NVMe format, those types of things. The actions we care about are down here, and the first action we're going to do is clear data validation. The reason is we don't know if this has been used before, and we want to make sure that all the data validation settings and the data validation table is appropriately cleared so that we don't have any accidental data validation errors. We choose clear data validation, and you can come over here and it gives you a couple boxes that you can check in terms of using all available unit paths, so on and so forth. Again, we are going to use just a set of unit paths. We're going to manually specify those. And so we won't worry about using all at that time, although we could. The next thing we're going to do is we're going to come back and add an action again. And in this case, we're going to add generic disk prefill. The thing that's really nice about the disk prefill action is I have the ability to fairly simply specify how I want to come out of my prefill. So if I want to prefill the drive 200%, I can. In our case, we really only want to do it 100%. But we want to make sure that we do come out of disk prefill only after we've written the entire drive. So we're going to add a couple zeros to the max fill time so that we don't come out based on max fill time. We come out on disk prefill, and that it hits disk prefill first. Once we've set disk prefill, we're going to go in and define the traffic that we want to prefill our drive with. And there's a couple critical settings that you will want to make sure you get when you do this. The first one is we want the prefill to go as quickly as possible. So we recommend that you change the Q depth from the default of 1 to 16 and go ahead and fix that. The last area that's critically important is to specify your data validation parameters and what it is you want to do to validate. So to do that, you first click the box on Enable Data Validation. And then you're going to click Validate Written Data on LinkUp. Oakgate has its own built-in data validation, so you don't have to do writes and then do reads and compare. We do all that checking automatically for you. And a big part of that is specifying the last writes to validate on LinkUp. As you can see here, the default is 1,000. What this does a couple things. One is, in any data validation model, it's much easier to troubleshoot if you can go from the read to the write where the validation issue occurred. And so to enable that, what we do is after every reset or pull power where you're linking back up, we automatically send out a burst of reads, and those reads go out and validate all of those last writes, and were they all correctly committed to NAND, and are they accurate across the whole write. You definitely want to specify this. If you are looking at a trace or something, even if you specified 100% writes in your traffic, you will still see this burst of reads that will occur as part of that data validation check, where we're going to send out a bunch of reads and validate that those last writes were in fact accurate. Go ahead and set this up. Now the next two boxes, validate LBA atomicity and validate outstanding IOs. These have to do where the drive has not issued a completion. This first box is going to check the atomicity of each LBA and make sure that the LBA is correctly written to fully. And then the last box will validate the entire IO. If your drive supports outstanding IOs, then you'll want to check these two boxes and validate the atomicity of those IOs, both at the LBA and at the IO level. The last part of this is expected behavior on trim. Here I can go ahead and set it as undefined. I can set all zeros, all ones, or not modified. So I have multiple choices in terms of what behavior I'm looking for, and ensuring that in fact that behavior is what the drive does as you go forward. So this will verify that behavior on trim. The second thing we're going to want to make sure we set is we are going to come down and do sequential IO pattern policy. The sequential IO pattern policy ensures when we are pre-filling the drive, we're going to do it with sequential IO, but as you come to the edge of the drive, the 128K IO may not fit in the little space you've given it. And therefore, if it doesn't fit, what we want to do is be able to truncate that IO so it fits into the required space and the entire drive is pre-filled. Always make sure on a pre-fill you go ahead and check this box on sequential IO pattern policy. And then we're only going to use a single profile here. And so we're going to come into this profile and specify we want to write the entire drive. We'll do that 100%. We want to do it as quickly as possible. And so we're going to do 128K writes. So the max and the min will be 128. And we're going to do sequential. And the last thing we're going to do is we're going to use the embedded LBA plus index. And what that will do is for that particular write, it will embed the LBA into the data pattern, and you can use that for troubleshooting. And that ends the defining of traffic. We should be all set. Your script is done and you're almost ready to go ahead and kick off your pre-fill, whether you want to kick it off from Python or in front of an exerciser routine or as the first step of a larger automation script. A couple things you will want to do though is you want to make sure that you go in and check your protocol and that it's set for what you want. In our case, we want it for NVMe. The other thing you'll need to do is bring your namespace over to the unit path so that you have your unit path set and ready to go. So with that, we're all done and we can run our script and pre-fill our drive and get the data validation all set and get ready for the next step. We now need to go in and define traffic. In our case, we'll do it within IO Exerciser. There's a couple key things from a data validation standpoint is again, within IO Exerciser, you're going to want to set your data validation settings so they match the pre-fill settings that we set over here. And so in this case, in this script, I set them up this way. And so I will want to come back and make sure I've got them matched. So this will continue the process now as we're running traffic. We can define the traffic however we want, and we would recommend that you start with very simple traffic and then you maybe progress to something much more complex like sub-4K IOs, which certainly stress the drive in the case of a loss of power, or extra large IOs, and the basic training will show you how to set all those. Now let's move to timed power cycles and say enable. And this is where we can start to define how we want to do traffic. And there's a number of settings that we can do. So the first is your power on and your power off duration. So we're going to say we want to keep it on for 55 seconds, and we recommend fixing these. And we're going to go power off for 10, and we're going to fix this. For PERST, I can do no PERST. I can assert PERST during the entire power cycle or assert PERST during the power cycle only. We're going to say during power only. And so this gives us the ability to go ahead and set these. Now I can also do composite power actions. So I can say I want to do a reset and then hit the power off. And in this, it gives me, okay, what type of reset do I want to do? And what's my delay between my reset and my power off? So if you want to hit the drive with a loss of power in the middle of a reset and see how the drive handles it, you can do that. I can also do multiple power toggles. So I can say, how many power toggles do I want? What's the duration between those? What's the number of groups? And what's the time off in between groups? So this gives you a way to do multiple, more tightly coupled power cycles than just a single power cycle that you see up here. Within the power cycle settings, there's a number of other things that I can also do to adjust the type of settings. So if you go to the Global Exerciser settings, general settings, you will see this power off. The first thing you will see is safe versus unsafe. Safe is not a normal shutdown. What this setting does is specifies, do I want to have Oakgate follow the hot plug spec and be able to protect the PCIe root complex. Generally, you're going to say, yeah, I want you to do that, because if I go to unsafe, then when your drive comes back on, if your drive has any tendency to spew stuff on the bus, it can corrupt the PCIe root complex and bring the entire appliance down, along with all the other enclosures that may be attached to it, running all of your colleagues' tests. So we strongly encourage you to use safe, but if you want to do unsafe, we would recommend doing that on a desktop appliance or something where no other peripherals were attached to it and you're running a controlled test in a controlled environment. In our case, we're going to go ahead and do safe. Now, I can also set the shutdown notification. So I can say it's a normal shutdown, which in this case is an NVMe shutdown. And if I quiesce traffic before and go ahead and assert PERST back in the previous settings, then that's going to be the exact same as a normal NVMe shutdown. I can instead say, I'm going to have the system set the abrupt shutdown bit, which is going to give the drive a little bit of warning that a power shutdown is coming when that bit gets set, and you can see how does the drive handle the abrupt shutdown bit being set. And you may or may not choose to quiesce traffic in that instance. The last option is no notification at all. You're still running traffic, and the power is automatically pulled from the DUT, and at that point you want to see how does the DUT handle that. So these are the settings associated with power, and those are the settings that will be applied when I do this power toggle here, whether I'm doing multiple power toggles or just a single power toggle, and I'm asserting or not asserting PERST, depending upon the type of test you want to run. The other thing you may want to do is you may want to also, as part of that, do resets. Maybe you don't want to do it right as a combined thing, but I can come in here and go ahead and set resets at the same time that I'm doing power, again as a timing sequence. And again, we recommend if you're setting these resets that you go ahead and fix them. So with that, that is how to do PLP testing and what we recommend. We hope you found this useful and interesting. Again, if you have any questions, feel free to send me a question on PLP testing or Oak Gate testing in general. And I hope you have a nice day. Thank you for your time.